So the important lesson from this is you need to not decide up front what your filter type is going to be and assume things about it, but instead measure the data and then try different ranges of filters and see what you get. Okay, going a little bit deeper here. Is anyone here familiar with differential power analysis or power analysis attacks? Oh, great. That's awesome. I wasn't expecting that. So template power analysis is an optimization of differential power analysis, where what you do is, if you're trying to discover a secret key from a device by monitoring the power consumption, there's a number of routes you can go. One is to go in completely blind and just say, I'm going to just measure the power consumption at the highest rate I can across the computation, and then try to look for varying bits based on the secret key. And that's what's called simple power analysis. Differential power analysis says, take a bunch of different sets of samples and average them together and compare individual candidates against that mean. Well, template power analysis is an optimization of DPA, where what you do is you buy a similar cryptographic device. So just go get a developer kit or whatever for a particular device and program your own keys into it and measure the noise distribution while computing things with a known key. And then you go get your device you're going to attack, which has a secret key, which you don't know. And you take that filter or that template that you developed against the known keys with the similar hardware and apply that to filtering the noise for attacking the unknown key. This is a very powerful attack. It can often extract the entire key in a single trace once you've developed a good template. And what template power analysis is focused on is you have a whole bunch of different filtering approaches. You have different filter parameters, and you just brute force through them, finding which ones fit best to the particular target. We did some analysis of jitter and different host configurations, but honestly, there's a lot more work to be done in this area. We want to know what's the best filter for network jitter in certain configurations. And anyone here who's a DSP expert or knows one is welcome to contact us. We'd be interested in hearing from them. Hypothesis testing. This is how you decide whether or not you found a difference. So here's some hypothesis testing approaches we looked at. The common one, Students T, it's a basic statistics class course. Basically, what you do is you look at the difference between the means and standard deviation of two distributions. And if there's a difference which is significant to a certain level, then you decide that they're different. Otherwise, you reject the null hypothesis and say these are the same distribution. Again, it works best for Gaussian distributions. The approach we actually ended up using, Students T worked okay for some particular configurations, but not generally well. We actually implemented the box test. And the box test is based on the percentile range filters we talked about before. What you do is you create a box which has a particular set of parameters between X and Y%. So let's say we choose 10 and 35%. For each distribution, so you've got two sets of samples, one for one guess and one for another guess, you apply the box to both of them. So you filter out the lowest 10% and you throw out the upper 65% and compare these two boxes. If the two boxes are strictly ordered, meaning the box that you expect to be less is on the left and the box you expect to be more is on the right, and they're not overlapping in any way, then you signal that as a difference. This is similar, if you could reword this as, in comparing it to percentile range filtering, you're calculating the difference between the peaks based on a percentile range filter for finding the peak. False positive and false negatives, standard thing. You want to avoid both. If you have too permissive a test, then you get false positives by saying they're different when they're not. If you have too strict a test, then you'll reject things which actually are different. So what advantages can an attacker have? A lot of people underestimate the ability of an attacker to choose an advantageous vantage point to them. Some hosts have more jitter than others, especially on the client side. We'll talk about what measurements we found, which host configurations had the most jitter. Others were extremely good, and some were good only at certain times of the day. And so when you have a high variability in the unfiltered jitter, you don't want that host. If you can avoid or model the jitter in some way, let's say you know a cron job kicks off on the server at 3 a.m., you don't want to run your measurements at 3 a.m. And also traffic shapers, you want to avoid those and have as direct and clean a route to the target as possible. So the internet is quite flexible. There's a lot of different vantage points you can choose. Even if they're all the same hop count or even greater hop count away, if they have a higher quality route to the target, they may be a better vantage point. There's a paper recently called Get Off My Cloud. Has anyone read that paper or seen that talk? Basically, it talks about what kinds of allocation do cloud hosting providers like EC2 or other groups apply in deciding where your VM gets physically located. And they found two interesting results. The first one was that it was relatively easy to co-locate your VM alongside your target. What they would do is they just repeatedly launch and stop their instance until they got onto the same host. And within a few tries, usually, they would be able to get onto the same physical machine. The other thing they needed, though, to perform this attack was to be able to predict the network layout of their particular target system. So what they would do is they'd use traceroute and other mechanisms in an automated fashion to map out the network and figure out how far are they away from the desired target. And the not so surprising result was that these providers don't make any effort to prevent these kinds of things, and it was relatively easy to do so. Great paper. So we looked at a series of vantage points. The ones we looked at were localhost, guest-to-guest in a VM, crossover cable, LAN, 2 EC2 servers that were in the same region but not on the same machine, and then from a regular DSL connection to a dedicated server, and then finally from there to an EC2 server as well. Here are our results. These are the minimum delays that were visible for us for each vantage point based on a certain number of samples. This will change based on how many samples you're able to take. So a few things about these results. The first things we did was we made sure to hold the false positive and false negative rate below 5% for our filter selection. And we used the box test with the parameters chosen by brute force between 0 and 95%. So we actually took all of our samples and 4 different sets of samples and ran it through. And what our box test brute force selector would do is randomly choose subsets of samples from the original set. So this was actually a sample size of 10,000 samples, and we configured the parameter selector for 9,000 samples. And what it would do is we would do 200 runs, selecting a random 9,000 set of samples from each distribution, and run the hypothesis test. If they were the same files, same sets of samples to begin with, and the filter said there's a difference, then that was a false positive, and we counted that against the filter. If, on the other hand, they were 2 different sets of samples and it said there's no difference, then we counted that as a false negative. And what we wanted to do, again, is hold the false positive, false negative rate below 5%, which was 10 out of 200. So for the most optimal filters for each configuration, the parameter settings were different. So for instance, for localhost, it selected different parameter values than for the crossover cable. And what we assume is that an attacker can profile either that host or similar hosts in the same style as templated DPA attacks. The attacker can basically find some other service it can query or something to be able to choose known values and decide how well they can attack unknown values. So for localhost and crossover cable, both were about less than 25 nanoseconds predictability. And then for LAN, it was about 40 nanoseconds. And we ran many, many tests to confirm that indeed these were reliable. These are somewhat conservative estimates. We had some measurements that were, say, about half or more these values, but we rejected them because they weren't reliable. A lot of times we would be able to distinguish it with the desired false positive and false negative rate, and other times we couldn't distinguish it. So rather than report 2 optimistic values, we reported conservative values. As you can see here, the EC2 to EC2 numbers were the highest in varying. We were able to resolve reliably down to 15 nanoseconds for repeated data sets, but only at certain times. So it must have been something to do, we think, with some of the scheduling on the same host or other competing loads or something. But basically, that value had the most variance. However, when it was good, it was very good, even better than some of our LAN measurements. So we think Amazon must have some really nice networking hardware up there. And for our dedicated hosts, it was actually very poor. We thought by getting a dedicated host, it would be idle and we'd be able to get good measurements. But it turned out the provider of that host had put it on a network that wasn't the best and had a decent amount of jitter, possibly due to firewalling. And so we only were able to resolve about 4 milliseconds, which is really bad compared to our other WAN tests. Again, DSL to EC2, we could reliably distinguish 20 microsecond differences. So then what we did is we cranked up the sample rate. And we haven't finished taking samples for all the data sets, but at least for the LAN, we were able to improve pretty significantly our results. So first of all, 500,000 samples sounds really big, but it doesn't take very long. On a LAN, it took about 15 minutes for each run of 500,000 samples. And what we found was that we were able to improve it to about 15 nanoseconds distinguishability by selecting 490,000 from the 500,000 samples and doing false positive and false negative testing. However, these numbers are still subject to review because we need to finish testing and taking more samples. The key thing to note here is that we were able to get a factor of almost 3 improvement just by taking more samples. So if in doubt, just take more samples. Early on, we had to reject a lot of samples. And what we found was that after doing some debugging and testing, we found that our own firewall was actually screwing up our internet measurements. So here are 2 distributions. One was a measurement of a 25 microsecond delta without the firewall, that's in black, and then the other one was with the firewall. As you can see, the firewall adds not only a significant amount of delay, the peaks are shifted by a few milliseconds, but also that adds a lot of jitter. The distribution gets shorter and wider. So if you have any problems, if you want to do any client attacks, what you want to do is do them from outside the firewall. Also, EC2 is really awesome when it's not noisy, but it can be really bad when it is. Certain sets of our samples were completely unusable, and we think this could be due to competing VMs. While the Rice University talk focused on competing processes on the same physical box, for instance, scheduling Apache processes, we think that the scheduling algorithm or something related to the Xen hypervisor that's used by EC2 may be more dangerous to taking good samples. However, when we did get good results, we would often get runs that were entirely composed of good results. And in those cases, it was comparable to our quiet LAN, in fact, often better than our quiet LAN. So they had better hardware there. Here's a distribution where you can kind of see the clear distinguishability of the two distributions there. We actually had a few things, strange things, continuing to happen along the way. The first one was that we ended up with a lot of noise that was added by the interpreter startup. So when we profiled different languages, Java, C, etc., C, of course, had very low overhead. But starting a Java VM is actually a pretty noisy event and would tend to disrupt our first few measurements of that system. We saw weird caching behavior. We're still not sure about exactly what those are related to. Possibly related to CPU caching and possibly related to CPU scheduling behavior. We ran into something earlier on where the equal and not equal operators in terms of comparisons seem to be behaving differently. And we had some questions about maybe that if in a particular language, if they're comparing strings with equals, it starts from the beginning. And if you're comparing with not equals, it starts from the end, because we kept seeing inverted samples. But it just turned out that we weren't taking enough samples for that particular configuration. So let's look now. We've looked at vantage points and said, okay, what's the minimal distinguishability from different vantage points for a given number of samples? Let's look at comparisons in different languages and see how exploitable these are. So we took some just basic CPU tests of a comparison operator in multiple languages and multiple types of comparisons. And what we did was we generated a TSC delta for a 1-byte comparison difference. So one value would be A, and the next would be AB, for instance. And we would see how long that took in terms of difference between just the A versus AB. So the interesting thing that we found here with C is that C, with the default settings, GCC compiles in its own built-in operators for memcomp. And memcomp is actually really slow in GCC. It's actually turns out to be a rep comp SB.